This book works, sound works right away. Okay, I'm happy to see you and sorry to hear if your previous lectures were hurt. Do you really need to go back to work at noon to some other? So I cannot use time after 11:50. You need to run to the next class. Okay. Yeah. It was like the schedule. I would do that 2 times instead of 3, and maybe a little longer, because we start from general chatting, and then when we all are warmed up, it is done. So basically, it is a class of warm-ups. Do you remember anything from the last time? No, it is fine. I don't remember myself. I'm just trying to cheat and get you to help me remember what was. What did you do?
We got up to taking the second partials of the wave equation, some cosine thing.
Okay, why it is needed?
Because you take the second partials, they differ by a constant. So 1 over, or no, is it like lambda over 1 squared times the second partial with respect to x is equal to the 1 over period over 1 squared with respect to times the second partial with respect to 2, something like that.
I'm scared to speak in the same room as you. You are too smart. Everything is correct. Yeah, thank you. It is a great help, and it is an excellent summary of what you did. Do you agree, or do you need to recite more?
4 pi squared, I suppose.
What?
I agree.
Oh, okay. No, I'm remembering a little bit, but not to a single digit letter and power and say, okay, something about wavelengths and 1 over wavelength squared. Impressive. Yes. But why do we need this wave equation? Who cares? Do any of chemists need wave equation?
Yes,
How come?
experience with it, and I guess electrons are light waves. They're, I guess,
I think one example would be like the gold experiment I remember a while ago, where they discovered how electrons can like split or something, something like that. Yeah.
Okay. Is there any connection to your fundamental knowledge about SPD orbitals? Like, would knowledge of wave equation help us to be professional chemists about speaking about atomic orbitals?
I think Curtis said it last time that the orbital shapes were defined by solutions to the wave equation or whatever, something like that.
Okay. And Cortis.
So
I don't understand that.
Who's for? Oh, the missing one.
Yeah, that was just always. That's correct.
Oh, okay. Well,
Hi. Okay, I'm having the same problem here. So like,
it's a good sign. You're on the right track.
yeah, you were even talking about that yesterday. So I recycled it.
Okay, so knowledge of the wave equation, or maybe do the little different equation will help us to get SPD orbitals as solutions. Okay. Can we like record your answer as final exam and finish the class, or we have some for the semester we need to do anything else? Of course, it's very tempting, but what do we need else between wave equation and SPD orbitals? Then we go ahead and just try solving wave equation for formula. how do you modify this wave equation to describe an atom or more? Right? Is it a good formulation for a challenge? No? Yes.
I mean, wave equation, like Schrödinger's wave equation.
Right.
We need like psi values, we need like a Hamiltonian matrix, all kinds of stuff.
Yes, like when we derive wave equation, it was basically a wave equation for a rope that I didn't bring last time, right? And
Yeah.
and it is kind of too much of extension to make an analogy between rope and atom. So we need maybe to bring in details about electrons in the atom. And even if the equation would be the same, there is no specifics telling what's like an atomic mass, weight, how the electrons are attracted or repelled from other charges, right? So this equation is correct in general shape, but is useless to answer practical questions of chemistry. Okay, so why did we chemistry in the class? What else? Do you? I think the best thing was to do interview one by one. It was mostly with your permission, I will continue. But the next question will be. It doesn't work. It's symbolic. I can't. Talking stick. Yes, exactly. Talking stick. The question. I'll start with Skype and go other way. So. Do you believe in wave equation? Do you believe it will be useful, or do you have any doubts? Is the idea that electrons behave like waves is natural for us or a little strange? Like, just try to share thoughts of yourself, not from.
I think it's useful that we can express the behavior in waveforms so we can predict behavior within electrons in certain space.
Okay. Yes. So, if you would doubt that electrons have wavy nature, why would you like? So many scientists had this doubt for many years, so it is very natural to doubt. How would you formulate?
It's kind of like because there's the other atomic model where they just kind of go in a circle. I just expect them not just kind of just be riding around like a circle, basically not acting on the wave at all.
Okay. So it is a conflict between common sense intuition and an idea to treat electrons like a wave. So common sense intuition, if you speak about charges, they are more like planets around stars, right? And it picks immediately our intuition, and we all are ready to believe it. And if someone is speaking about waves, or today we all are modern people, but like 100 years ago or 150 years ago, it would be like someone very theoretical. Okay. So, why anything on this?
Can you repeat the question? Like, I don't know what I'm supposed to know.
Particle wave duality for electrons, not wave waves. Like anything that you do, why arguments to believe that electrons is a particle, arguments to believe that electron is a wave. And then we could okay, that's because why?
I mean, electrons, I guess, have nodes the same way a wave. And if you're using the wave equation, because you can solve for what is happening at that specific node or the value.
Okay, let me play a critical game. You mentioned electrons demonstrate nodes. How do you know? Did you see yourself? Did you measure yourself? What do you do with somebody?
I guess they can act as a wave. They have the same, I guess, actions or I guess, behaviors of what a wave can do.
Okay, and what are the evidences?
I
I'm totally.
I have SP orbitals.
Okay, but have anyone saw SP orbitals? Or we just read textbooks? Okay, so if textbooks do not lie to us, then electron maybe have wavy nature, but it is more abstract concept rather than our everyday experiences. Okay, good. I think I'm out of questions. If it is okay. Okay, I'll just look on slide and then start interacting more. It was so deep discussion. Thank you.
No, I can't. I'll bring that back. I didn't know.
So from time to time, I will be sharing this links to recordings from previous years. If you can compare, you don't need to have them. It just one can go forward and see what you did like next. If you're so dedicated, each and every expect. Here are some optional reading that will give you far above what we discussed here. And here is what we did last time, right? Do you recognize it? So we check if this equipment works. Not quite. I better wait. So it's maybe not writing, but only marking things. So we had a standing wave. We arrived to a standing wave based on discovery from James, right? And his discovery is based on, as we will later see, Euler equation and trigonometric conversion of sum into product, right? And then we saw that there are points where amplitude is always zero, and there are points when it oscillates. Then we did an experiment, mathematical experiment, that second derivative over time and space coincide, right? And here is an interesting observation. Like on the left, one has 1 over period squared. On the right, one has 1 over wavelength squared. Why don't we multiply left and right by wavelength squared? Here, put 1 squared here. Then this term can be lambda over period squared, right? So length over time, what is length over time? Distance over, huh? Yes, everyone agrees, right? So velocity of what? Yes, so it would correspond to velocity of the traveling wave that later has generated the standing wave. So when we have this like rope or trace of a stone on the water, it moves with certain velocity, right? And if one composes a ratio of the wavelengths over period, it will show how quickly it moves. So wave equation has second derivative over space and time and wave velocity, right? But here we do not have, it's like free waves with no obstacles in the middle, right? If the electron is considered as a wave, it has a major obstacle. It has an attractive positive ion, and the properties of a wave will be different near the ion and away from the ion. should probably modify the frequency. It should be trapped and not going away. And it is one of the technical goals of the course to learn how to. Equations are too complicated. Half a year is not sufficient, but you'll get general principles how to interpret and how to approach solving these questions, probably with some computational tools. So what if, like, even you have a, let's say, cation, and then in the electrochemistry experiment or in a vacuum, there is a charge that is getting trapped by this cation. How it is getting trapped? What changes for the properties of the electron that is getting absorbed to a molecule? Okay. Did you ever have you ever seen the non-flat TV? 1, 2, 3. Okay, majority. Who haven't seen non-flat TV? Okay, so in the if I would be prepared in a due manner, I probably should bring this big box, like a glass kinescope that shows something on the screen. How does the ancient TV generates light? What does it do?
Cathode ray tube TVs.
Yes.
So they beam. So it's a cathode ray tube, like the olden days. They shoot a beam with electrons into two magnets with changing currents to generate a chain. You can control where the stream of electrons goes. The stream of electrons strikes the back of a phosphorescent film that generates the image on the screen.
Okay. That's great. What is this phosphorus? Which material? Some instead of phosphorus, sometimes they call it
Phosphorescent, I guess. It just generates light and then it stays for some period of time before it's clear.
It's not a difficult speech, you just cannot pronounce letters S and C one after another. No, imagine I'm doing it S, C, and then insulator. Insulator. Insulator.
Insulator, I don't know. Understand that.
But it is exactly what you mentioned. So when it is being hit by electron, it's getting excited, and then it emits photon. And one of the cheap examples is zinc selenide, which is a semiconductor. It has an energy of set between home and home, and when you promote it, you dump back. But there is a lifetime, and then when the electron ray scans different points, it gives, it doesn't give light because the intensity of the electronic ray is modulated through this broadcast signal. Yeah, true experiment demonstration. Sorry, the seat is occupied. Good. That's okay. That's okay. Please keep coming a little later. Then I will be feeling myself much better coming late as well, knowing that I'm not the latest one. So the screen here is powdered from inside by this scintillating thing, and then there is a electronic gun that just gives a ray. Huh? Yeah. And then if it hits the surface, humans may observe it by converting kinetic energy of electrons into the photons. So now the next little thing, if one creates a blocking layer that doesn't allow electrons to go through and then punches a hole. So through a hole, there will be almost straight ray, and there will be a spot on the screen. Then if you do a second hole, we expect from our common sense, then there will be straight ray, and there will be another spot. Do you see any shortcomings, anything wrong in this trade of thoughts? Or more directly, what is wrong in this paradigm?
Not necessarily from an intuitive standpoint, but assuming electrons behave exactly like light, that it's going to make the fraction pattern on the back instead of just a straight line. Because of
You're ready to final examination. You don't need to sit here. Let me interview how the great ideas of James are penetrating through the class. Yes, I was remembering that two letters are duplicated in the name.
yes,
2 R's and 2 T's.
2 R's and 2 T's. Yeah, okay. I'm on the right track. So, would you like to oppose him or support?
I would support him, because this diagram assumes that the electrons are just acting as particles, but if they acted as waves, they would show constructive and destructive interference by a probability distribution. That across the screen.
Gorgeous.
Curtis.
Gorgeous. I may be a little earlier than 1 month, but no guarantee before. So anything in support or opposing?
I don't oppose, I agree, but I don't really fully understand.
Okay. So can you formulate what you do not understand? Like just share how you envision what is going on and what is what you're.
Well, if they're, I get like how if they're waves, they would have constructive and deconstructive interference and they would affect each other, but I guess yeah, that's as much.
Okay, yeah, thank you for the discussion. So where is the trap? You all were correct, and I accumulate your wisdom during the class. So if we believe that electrons are particles, then they are going on a trajectory, so likely straight trajectories. Maybe they're slightly deflected by magnetic field or gravitational field, but if they are shot from this electronic gun, it is a like straight line. But if it is a wave, then we cannot speak about straight trajectory. There will be a little natural spreading, right? And the phase of a wave in each point of this spreading will be different. So instead of going directly here, it will be a little width of a spot, and there will be an area where the widths of one and another spot overlap. And then we do not know at which phase the wave will come from slit 1 and slit 2. Depending on the position, it may come with positive or negative phase, and they may experience different pattern. Make sense? So there will be bright spots in the center. And our discussion went too much advanced. I didn't expect it. I thought like playing toys, showing experimental facts, and maybe leaving conclusions for the future. But it is something that one can observe, and it is one of the proofs that electron has a wavy nature. So if we would believe classical picture and electron as a particle, this picture would mean that it just goes through the closed gate and makes a flash in the middle, but it's closed for sure. So it is a deflection of rays and coming in with different phases. It took me 10 years to copy paste this figure from the Wikipedia because it is moving. So it is basically what is going on if we have the wavy nature of a particle. So each slit should be considered as a point source of radial waves. And yes, maximum will come directly parallel to the place where a spot is, but there is a substantial amount of waves going upwards and downwards. And if they come together, you see this positive and negative come in a pattern. Yes.
So if there was just one slit, would you just see like brightness parallel to the point and then kind of get dimmer as it gets away from that?
Right. This is a very deep question. It's scary deep. So when a wave comes to a place where it interacts with something else, this interaction doesn't know about phase of a wave. So a single wave may come with positive and negative phase. But if there are two waves, this positive and negative may get constructive and destructive interference, and then it's not a phase, it's amplitude that is getting better. And then therefore, even if there are different phases of a single ray here, one will have a spot without fringes. But with two slits, there will be fringes. Oh, okay. This do you remember we were talking that there will be projects in the class, right? And here are the couple of movies made by students in the class. So here is our talking stick. L's and A starts with A. Ellison. Anna. Sorry, I'm okay. So Anna, what do you see and how do you interpret?
Well, we can see like all the different models, they're all moving at like different rates, and like the different shapes, they're like repeating themselves, and they're all going in like a consistent pattern
Okay.
around like the center point.
Absolutely great, thank you. And the question is a little, I wouldn't say trap or provocation. I was just asking a question without giving due explanation, trying to do my job. But thank you. Starts with E.
Right.
Elsa.
Emma.
Emma. Okay. E. A. Emma. N. Okay. So. Emma.
Yes.
I was just blanking. Okay. Can you say by your own words what is oscillating, why it is on the circle, what do you think it may model?
Well, I see that the Bohr model is highlighted.
Oh, okay.
Yes, that.
Oh, nice to be literate.
I honestly, I don't know. I'm sorry.
We all know very few things. Just share what you see and what you think. If you give me a little directions, what I need to say.
I saw the same thing that on it did, honestly, but
But if something is oscillating, right?
yes,
Do you see on this circles they have like degrees,
right.
right? And there is a thicker line in the there is a little thicker line, right? How do these oscillations behave in respect to the thicker line? Are they going outwards and inwards? Basically what I wanted to hear. Okay, excellent. Let's run this one and continue the discussion. This one is a little different. I hope you remember the room name. Oh, Justin. If JJ. Yep. James Justin. If you want to improve, you can just sit in different places and all my picture will be broken. EAJJ. I'll continue to make them up. So, Justin, what do you see and how do you do? I guess from what I've heard, it's more monos, oscillating monos, I guess. But are they all beautiful or some of them are ugly?
Yeah, I don't know, the top right one, you know. This.
Okay, tell us criterion of ugliness or beauty in context of this class with genuine.
I guess,
Why do you decide that it is ugly?
well, okay, so I guess the bottom left one, I don't know, it's got smoother lines.
Yes,
Yeah.
yes.
And then, which I guess, I don't know what those mean.
So smoother lines are more beautiful. And this random noise is ugly.
Yeah.
Great, I'm completely with you. Excellent. So, this illustration is a little ahead of time. It's more like outcome rather than foundations. But suppose we, Spencer, did mention the circular orbits of an electron, like a planet around a star, right? And there is a concept of Bohr model that we will recite in like about 40 lectures, closer to the end, with more details. But it was a dramatic this is not dramatic. It was a dramatic breakthrough in knowledge of the humankind, the conversion of the mindset from classical particles of electron to waves. But this transition was not instantaneous. It was several steps, and Bohr model is an important step in between. So it is half particle, half wave. It has some properties. So on one hand, Bohr's model assumes planetary model, so that something is going on, electrons go on like circular or elliptical orbitals, right? But on the other hand, they are considered as a little ropes, as we missed to play last time. So that around nucleus there is a rope, it is shaking, and then it demonstrates standing waves. So now if you haven't heard about Bohr model before, now your imagination will be shaken and impressed. If you did hear, maybe not. So only those energies of standing waves, or on energies of electrons that generate beautiful standing waves, are allowed by Mother Nature. So the beautiful waves do exist in Bohr atom, and ugly do not exist. How do you like it? And here how one thinks about it. If the wave goes on a circular path, and it has certain wavelengths and frequency. So if one can match integer number of wavelengths of oscillations, so it is 0, negative, positive, and again 0. So if it is an even number of full oscillations, and then it goes again 0, negative, 0, positive. Second, so 2 full oscillations. Then after a full circle, it comes to the same value as it was before. And then after making a circle, the wave repeats itself. And then there will be smooth lines. It's like it doesn't interfere with itself, it repeats itself. It is a beautiful standing wave that is allowed by Mother Nature for hydrogen model of hydrogen atom by Niels Bohr. But if the wavelengths, which depends on some other parameters, we are not going to discuss it at this point, if it gets fractional number of oscillations, then it is like a snake starting to eat its own tail. It will come with different head and tail, will come with different phase, and the wave will interfere with itself and create this ugly interference picture. And the idea of Bohr was just ugly is not allowed, beautiful are allowed. And then the amount of periods, amount of this number of wavelengths do depend on the energy. So like lower energy electron has less, smaller wavelengths in the terms of this picture. We will be very precise in like 3 months reciting. Higher energy will have more denser fringes. But not any energy is allowed. Only certain values of energies that generate beautiful pictures are allowed. And then one comes to, from this hand wavy arguments, one comes to an idea that energy is quantized. So in hydrogen atom, there are only certain energy levels. Not all of them are allowed, only certain, right? And then one has optical transitions between them, and one has very specific spectra of each element. It has lines rather than bands. So only specific transitions at very specific wavelengths, very specific wavelengths are allowed. And the idea is this interference. Any questions about this stuff? Was it boring? Was it entertaining a little bit? Okay, good. I'm okay. Thank you. So we are not focusing on the Bohr model right now. There will be dedicated full lecture with all details, but we need to pick up some concepts and then generalize them. So I cannot keep them three. We need Schrödinger equation, but postulating and just writing down equation will be taken either with I have forgotten the citation, but it is about a group of scientists have taken ideas of others, other scientists. It is taken either with ignoring with a cold attitude or rejecting with a hot attitude. So if you just postulate Schrödinger equation, you just decline to take it or start arguing or do not care about it at all. So it will be too early. Although it is a main equation of this course, we need to lay foundations before we can speak and appreciate its at most beauty, at least its usefulness. And it is a very deserving sacrifice to spend about 5 meetings to lay foundations and start speaking on the quantum style of language before we go into equations. So a little foundations for the Bohr model, which is, well, you can say it is wrong. It is just an intermediate trampoline, and it is a step in a human knowledge development. It is not a practical model for solving problems. Once it coincided with experiment, but most importance of Bohr model that it gave a way of thinking that broke an old style of thinking. And then humankind was ready for actual quantum mechanics. So one assumes, maybe I will be a little not humble, but I will focus camera on myself. Then when we will go to discussion, I will return. I should stand here. So I want to believe that you accept the general concept of the Bohr model, right? About beautiful and ugly trajectories. Now, something is oscillating as electron is revolving around this orbit, right? And one needs to quantify what is oscillating in the Bohr model. It is wave of what? Some of you already were reading about quantum theories and you speak about waves of probability, but how do we know it as a humankind, how do we know it 120 years ago? So it is a challenge. What is oscillating? Even if you accept that there is a beautiful and ugly trajectories, like what is oscillating as electron is revolving around nucleus? On one hand. On another, how to quantify the circular motion? How to what's the difference in this ugly, beautiful and beautiful waves of different energies? So energy and velocity are not appropriate for circular motion. There is, because like velocity is changing, right? Its direction changing. So one needs a specific observable, specific way to quantify circular motion. And this tool is so-called. Are you happy with angular momentum? Are you hating angular momentum? Don't hesitate. Oh yes, it is like I can tolerate it, but I do not like it specifically. Okay. So angular momentum is a way to quantify circular motion, right? And it is, and you are finding this cross product, right? So if one connects origin of this motion with a point of stuff that is moving and makes cross product of the so origin r and here momentum, and r and p are in the same plane, then the angular momentum vector will be going outwards of the plane, right? And if you be the longer, the quicker is rotational motion. So here is the way how Bohr formulated his ideas about beautiful and ugly trajectories in a more algorithmic mathematical way, because he was writing papers and talking to scientists, not to artists. So the concept of beautifulness was not as useful. So he told, like, let's assume that angular momentum divided by 2 pi should take, and divided by a Planck constant that was already designed by this time from thermodynamics, will take integer values. 1, 2, 3, 4. So if they are integer, it will be allowed trajectories, which will give beautiful shapes. If they are fractional, they are not allowed by nature. It is a more algorithmic way. Okay, more or less done with this. Accepting? No? If there are questions, please formulate. I would prefer to discuss simple concepts rather than go into next complicated. No?
Why is the Planck constant in there?
Who asked this question? So thermodynamics and statistical mechanics was developed before quantum, and there, like, thermodynamics is what we start in high school, but statistical mechanics is probably you had a little bit of it, or you plan to have it in next Econ 2 or stuff like this. So there one speaks about ensembles of many objects of the same nature, like Avogadro number of objects. And then each of the objects, the simplest thing is like individual atoms, maybe noble gas like argon. And then each of the atoms, the classical, has its own position and momentum. And we need to speak about properties including temperature. And then instead of Cartesian space of point positions, we speak about phase space, where one has both positions and momentum. And one needs like what is the properties, individual property of a single particle that contributes to ensemble by browsing through where it is located in a phase space. So one cannot survive without determining momentum and speaking about it at each point of time. If there is a motion, if temperature is involved. And then there were several discoveries showing that properties of ensemble are related to universal constant. It will be too long if I go into details. But this universal constant has a dimensionality of position multiplied momentum. One of the examples, one can theoretically reproduce the spectrum, emission spectrum of sun, and the parameter of the spectrum is Planck constant. One can basically fine-tune the value of Planck constant by fitting to the solar spectrum. Enough?
Yeah.
Okay. So 2 minutes for most complicated part. So what is going to change? Why? How? Right now, I assume you accepted this. Integer number of what? So what is this phase phi that accumulates during the trajectory? Is there a way to speak about it in more quantitative way? So things are written here. And the best thing is to read the lecture from Richard Feynman that I gave a link to. It is not necessary absolutely, but if you want, it will give you something. So classical particle performs trajectory. It has kinetic energy, which is mass velocity squared over 2, or momentum squared over 2 masses kinetic energy. It has potential energy. If it is like harmonic oscillator, it will be delta r squared over 2. But generally, if it is in the gravitational, it will be mass gravitational acceleration height, right? Potential energy. And Hamiltonian is, some people use T for kinetic. Kinetic plus potential, right? There is a crazy French man, Lagrange, who thought one needs to subtract kinetic and potential. And if one subtracts kinetic minus potential, it brings to a very bright discovery for classical mechanics. It was done at the time of Napoleonic Wars. I'm just lazy to write a few more equations. So if one formulates the subtraction of kinetic minus potential and writes down an equation is derivative of a space over velocity and over time, then this equation applied to Lagrangian will regenerate equations which are very similar to Newtonian equation of motion. Those Lagrangian equations are more general. They will work in situations when Newtonian equation of motion is very hard to derive, and when things are going counterintuitive. If there are like mechanical engineers use it for like connected pendulum, rotational, and many degrees of freedom, it works better. So if one integrates value of Lagrangian along the trajectory, it will give from initial time to final time, it will give an observable quantity that is called action. And here, we are basically done. Last sentence. Everything in Newtonian mechanics can be redone. So instead of solving Newtonian equations, one can random generate a trajectory for any object. And only those trajectories that have minimal action, least action, are allowed by Mother Nature. And like instead of doing homework, which you don't have to do, or preparing lecture, I prefer to lay on a couch. I prefer least action. because I'm part of a nature. Okay, meeting is done. No homework. Looking forward to see you on Wednesday.
So for that example, right there, I'm not here. So what is over there, but the total derivative is similar, is that way or is that? I don't understand how it's affecting those. Okay.
I'm going to stand on to appropriate on that.
Rules, one is missing one partial symbol in here. So it should be DL or DP. And then one should fix it by putting mass in the right place.
Wait, all right, so what is this little bit equal? Let me just write it on the board. Where was the thermal component? So partial of L strike X. Other marker destroyed.
I have a better solution instead of writing. We can just go line.
Is V, so is V the potential or is U the potential?
It's just semantics. How do you code?
Okay, because the potential is, so we were talking about potential and
Yes, yes.
as a function that we could find another function for, which would be conservative. How it would be path independent along that path, I suppose.
What?
Now we were talking about how the potential is a good example of using conservative vector fields.
It's,
LQ dot.
I'll start sharing so that you do the recording just in case we need to watch this.
So it's Q dot, so it's the derivative of Q, so it's with respect to time. Oh, so a D is missing down there.
Yes,
Okay, so it's partial of the derivative of Q.
right. Yes.
Okay. Can we go back to the slide then? Because that is much harder to understand than this. Okay, so it's just a D in there, parentheses around.
Yes, yes, exactly. A little D is missed. Thank you for catching it.
Okay, I was just partials. And this is talking about Lagrange mechanics with calculus of variations, right?
Mm-hmm.
Trying to find which path
Mm-hmm.
in the system
Yes,
has the lowest integral value, I suppose.
right. So it is in a way of solving equations, it's not much different from linear equations, mostly you solve differential equations, but it is a different way to formulate equations. So instead of second derivative of position equals force, right? You do this combination of derivatives over energy or Lagrangian, and when you solve, you get as a solution x is function of t. But this equation follows from least action principle. So to get this equation, one just declares like for any trajectory one can set up on find the action. And only those trajectories that provide minimal action are will be realized in experiments in nature.
That makes sense. So the lowest line integral, I suppose. This is a parametric curve that we're talking about.
Mm-hmm.
So variations of a parametric curve.
Exactly.
That checks out. And for the, I suppose, so the whole point of this lecture was basically energy is a discrete variable. We're not treating it as a continuous one.
No, it's not. I cannot say that it was the only and single goal of the lecture. We need to derive shredding equation. And to derive shredding equation, we need a concept of epsilon values. No, we need to derive time dependent shredding equation.
Oh, okay.
And when it's very hard to do without concept of action. So by applying to action as the theoretical concept, it opens us a path towards derivation of time dependent shredding equation.
Okay, well, you can go for a second.
Oh, I just need a quick clarification on cross product thing. I'm trying to remember what the negative.
There's
It should be negative J.
Negative J?
Yeah, negative as for the, yeah,
Okay.
because it's, yeah, honestly, you'll find a formula if you look at the cofactor expansion.
Oh, okay.
It's
Yeah,
like
no,
how
it's
you
been
take-
like, it's been like 4 months since I've done a cross product.
do you have a question? No?
Yes, we do.
Okay, we'll locate in a second.
Yeah, no worries. And this, all of this is on the slides that we have, right?
Yes.
Sweet.